Hello everybody, and I'd like to thank the organisers and also Eileen for allowing me to come on after the last speaker. What I'm going to talk about today is really a question of business development from a more sort of scientific point of view about how you can bring technologies in to address issues which are facing the bioprocess industry today, and how an organisation such as the Qatar Foundation and the opportunity we all have as companies either established in this place or hoping to become established in this place can really work together in a really flexible way. And flexibility could be the mantra for this talk. So what I want to talk about is the bioprocess. And the bioprocess, we generally say, is how do you make a drug or a vaccine or any kind of therapeutic molecule in a way which is efficient, cost-effective, provides value for money for not only your investors but also for the people who are actually getting that drug in the end. They get it in a timely manner, in a way that actually makes a meaningful difference to their life. So I'm just going to sketch how I see the bioprocess, which is really a workflow of units of work which have to be done in a timely fashion, in an organised fashion, and have to give you meaningful and usable data that then can be used into the next stage of that process. So if we just glance at this, we can see that we would start out with initial DNA work. We identify the protein of interest, be it an antibody or a subunit vaccine. We take that, we clone it into our vector, and our vector could be anything from a virus, it could be a bacteria, it could be a filamentous fungus such as Neurospora crassa, it could be anything up to Percy6 cells, which is the human cell line, which people are using a lot now. And you have to do all kinds of stuff. You have to do restriction enzyme mapping. You have to check that your vector has received your insert correctly, that your promoters are correctly situated. You might even want to sequence that thing to check that you've got the final correct sequence and insert, or if you've been doing any genetic manipulation on it, if you want to enhance particular aspects of it, maybe knock out a protease that could screw up your protein production, you might want to do DNA sequencing. Once we get to the actual protein production, we can largely split this into two phases. One is the small to medium scale bioreactors, which is optimization of your fermentation conditions, which relies on looking at how much protein is being created, looking at stuff like phage contamination, looking at the media. What is in my media? How well is my media performing? How is the quality of the water that I'm putting into that media? Physical parameters such as what is the pH of my bioreactor, what is the percentage of carbon dioxide, the temperature, the oxygen, all of these things are vitally important. And at this time there are very few systems that can be used to monitor these in real time. We often find when we're talking to customers of our company that people say, yeah, I'll look at that and then a week later I'll get back the data. Well, a week later the data is useless. Now the final stage of this is the large-scale bioreactor, which as we know can go up to 2,000 or even more litres of material. And here again we're looking at the same sort of thing. We're looking at protein expression monitoring, but we're also starting to look at the QA/QC phase. How are we going to get that protein out of that bioreactor to where we can get down through purification to QA/QC, right down to fill and finish, and getting it to the customer, to the patient in a timely manner. Well, this presents a huge dilemma. These are the applications that I've just touched on, and this is probably about half of the technologies which are currently being used to monitor all of these different applications. And we go from everywhere, from gel electrophoresis, right down to something like the 40-bio octet, to capillary isoelectric focusing, qPCR, etc., etc., etc. And the point about this is, you've got 20 or 30 technologies for which you are trying to extract information in a timely and meaningful manner. And all of those have bias. All of those have reflections of their own detector system, their own dyes, their own modalities. And all of that brings more confusion into your system. So what we're trying to present here is a view that you have to limit the number of technologies that you use in your bioprocess in order to expedite in a timely fashion this process. Now, time flies. You don't have a lot of time. This is planet Earth. From January 2004 to just after 2007, this is the spread of bird flu. So these are the clusters coming up. And you see we start out in Southeast Asia, but within a very short space of time, we're right up into China and Russia and right across to Europe. We've managed to, nearly down in Qatar. The point is that represents a 25-month period. You do not have time to start doing huge stainless steel constructions of fermenters and such in a typical state-of-the-art. And here we have the state-of-the-art at this time. This is just a variety just pulled off Google. This is from Sigma Aldridge, and these are a couple of academic stations. These represent hundreds of millions of dollars worth of investment of fixed plant. If a new strain of HN51 came along, this is all useless, because it would take you months to do what's clean in place and steam in place, to get these into a state where you could then put in your new vaccine, which we all probably understand is going to be the easy part, is actually making the vaccine, identifying that molecule. But producing it in sufficient volume is going to be what's going to cost people their lives. And that, at the bottom line, as me and my colleagues have been discussing today, we are here to save people's lives. That's it. So what we have to do is look around us and see where we can get strategies to ameliorate this situation. And in our company, we've been working with the Department of Defense and with DARPA in what's called a rapid manufacture of pharmaceuticals program. And we draw from that. This is actually a slide credited to my colleague Pete Latham from BioPharm Services. We draw from this experience in the biodefense market, and we look to see its application in the biopharmaceutical market. And here's the deal. You're looking at time to market. I mean, I'll leave you to read all the little things, but the time to market here is 7 years. I've just shown you the spread of bird flu, which is spread by migrating birds in over a 25-month period. We all know that the flu pandemic after the First World War killed more people than the First World War, and that was without commercial jet air traffic. It was all by ships. So over 20 million people lost their lives, and it was all just being transmitted by ships. Let us consider what would happen with 747s with 300 people in, flying back and forth 24 hours a day. We have to get our speed significantly up from 7 years. We have to get it into the month scale. If we do not do that, we shall be in trouble. So if we look at a biodefense pandemic response, we don't have time, we don't know exactly when it's going to hit, but we do know that we've got to treat entire populations, and we've got to be flexible. Cost per dose is vitally important. We were informed today that you can have all the money in the world, but you don't actually have access to the vaccine, but you also have to be able to pay for what you do have. Because if you can't, again, your people die. Technologies which are proven in biodefense are applicable directly into the modern biopharmaceutical market. And this is where the situation we're in here in Qatar is so vitally timely, in that this organisation, the Qatar Foundation and the Science Park that we are all helping to create, is in a unique position. Is in a unique position, I'm going to skip that one actually, is a unique position to actually leapfrog these old fixed technologies that I've just been showing you. We are able to, through sound business development, to cherry pick this unit from here, this unit from here, this technology, and put them together just down the road in a way that can really change the way we create biopharmaceuticals. The capital infrastructure is reduced because we are not building fixed steel setups. We are not spending time designing plumbing, making concrete set, putting in stainless steel. Again, it reduces our cost of goods and opens new markets.